Welcome back, Ramda people. We're going to pick up with the t's. So the t function stands for true. It's the function that always returns true. Any parameters or any passed in parameters are ignored. Thanks for spending your time with me. Tell a friend. No, I'm just kidding. Um, there's not much to say about this. There's also false, which was looked at in the original series that Chris did. Um, the only thing is you do have to call it like a function, so you have to invoke it with parentheses. But any parameters you pass in are just completely ignored. So what this is the same thing as r dot always. It's the constant function where you pass in true. But of course here it's just t. So if I call it like that, I just get a function which takes no arguments. In fact, if I do dot length, the length of the arguments is 0. If I call it, I get true. If I call it with 42, we know that's true. But so is 420, yeah? Or false. Doesn't matter. You're going to get back true. And where this can be useful is if we go to condition, which is like Ramda's switch statement, and they're actually using it in the example. I don't have to type it. Yeah. So they call this function. So if I call the function with 0, it water freezes at 0 because it hits this condition, and if equals 100, but if it doesn't, if I applied the function to 42, I get this last case. Nothing special happens at 42 degrees Celsius. Um, but the key is that it's checking this one to see if it's true or false, and then it's checking this one to be true or false. And this is like our default statement. Um, if it's not these, then it's this one. And in order to make it true, we use the true function, and that makes it true. That's one example of where that can be useful. And then we move on. And we've already done tail. Tail is the all the elements of an array except the first one, and all the characters in the string except the first one. And then the opposite of that would be init, which would be all the elements of the array except the last one, or all the elements of a string except for the last one. And then head is the first element in the array, and last is the last element in the array. And we move on. And now we've got this take function, which is kind of cool. Um, we've got our d.list coming from this sum data, which is a list of 1, 2, 3, 4, 5. And we could take 2 from that, and we get 0, 1. No, we don't. 1, 2, 3, 4, 5. Take. Oh, well, let me slow down. It takes a number and a list, and that's why we take 2 from the list, and we get 0 and 1. Or sorry, 1 and 2. The list starts at 1. Um, so it takes a number and it takes a list and it returns a new list. It's a little like filter, a little like drop. No, I say a little like drop because I see drop here. And we might have looked at this in the first series when Chris looked at the drop function. But it could also take a number and a string and return a string because in Ramda, strings are just like arrays of characters. Um, it returns the first n elements of the given list, string, or transducer, or object with the take method. So we're not going to worry about that end. We're just going to say it returns the first n elements of the given list or string, and that's what it does. So of course we have to use this example. We have personnel, and we want to r.take 5. If you get the reference from the personnel, and we get Dave Brubeck, Paul Desmond, Eugene Wright, Joe Morello, and Jerry Mulligan. So cool song if you've never heard it. Um, take 5, and then we could partially apply that. We could make a function called take 5, which is the partial application of take with the first parameter of 5. And then we could just say 5. And what do we got? No, I keep doing this. My own function called take 5, and we get the same arguments. So I think this is like one of those in functional libraries that you got to have a take function. We could slice. I wonder if they use slice. Good look. Yeah, slice 0. If n is less than 0, then we use infinity as the second argument to slice. So slice from 0 to the end. If n is less than 0, otherwise use n. So slice from 0 to n, or if n is less than 0, start at infinity? I'm confused. I gotta work that out now. So, oh, can you go backwards? Okay, returns a list of. Do they use that? No, they don't use that in the example. But let's say we're going to take -2. I'm still going to call it take 5, even though that's not what we're doing here. And we get nothing in that case. I wonder why they did that. Maybe it's just a way to prevent errors, I guess, if you pass it a -2. There must be some reason for that. Because if you're saying if n is less than 0, then we take infinity, which means we're going to take the entire list. But if we just do take +2, we're just going to get 2. Dave Brubeck and Paul Desmond, who I think are the two musicians that wrote the song Take 5. Yeah, okay. And we move on. So take last, number a list and returns a list, number in a list and returns a list. So the exact same type signature. This one returns a new list containing the last n elements of the given list. If n is greater than the list of the length, then it returns a list, the length. Okay, we'll have to look at what that means. Let's keep our array here because we also can do strings. And we want to take the last, take last, let's take the last 5. Take last 5. And we get going from the bottom to the top, Ron, Joe, Bob, Jerry, and Joe. And then we don't take the first 3, or I guess the last 3, because we're starting from the back. So that answers my previous question. Can you pass in a negative number? If you do, it just ignores it. But if you use take last, you can pass in a number. It's not negative, but it's essentially the same. You could also reverse the list and just take that, and that's probably what's going on. Let's look. Oh, it's using drop. So we should probably go and refamiliarize ourselves with drop. And before we do that, it works with strings too, but just pretend strings are arrays. Um, yeah, let's go look at drop last. Let's look at drop. Drop takes some numbers. It's the same type signature. Returns all but the first n elements of the given list. Let's look at drop last, actually. Returns a list of all but the last n elements of the given list. It's just really just an alias because I don't see anything different. Yeah, no, it's the exact opposite. We don't take the last, we drop the last. That's what's different. So if we go back to take last three, we get MDA. Let's just do it. Take five personnel, we get these last five. If we drop last five, oh, oh, drop last. There we go. Then we get Dave, Paul, Eugene, and then we drop the last five. So drop is the opposite of take. And we've got two more take ones. Let's knock those out. The take last while. So again, with these, trying to be consistent with the naming, by looks for a value and does something by that value. While has to do while something is true. So both implementations, whether we're passing in a list or a string, we take while that A satisfies predicate. And these are really useful because you don't need a separate function um, to guard against operations. You can do it all together in one go. So this returns a new list containing the last n elements of a given list, passing each value to the supplied predicate function. So for each A, we pass it to the one at a time to the predicate function and determine if that A is true. And if it is, then we take that last thing. And then we've got take while, and this is going to be the same, but it just goes from the beginning instead of from the end. And then it says drop last while. So take while, drop while, take last while, drop last while. They're all um, they're all similar. And this one works with the add index. So we'll look at that too. But let's assume that we're looking at take while and take last while together, because the only difference is which end of the array it starts at. And of course, we could just use take while and reverse the list, and that would do the same thing as take last while. So get rid of that partially applied function, and we want to take last while. So we need a predicate function, and why don't we say while the item includes an e. So our predicate would be r dot includes lowercase letter e, and then we need a list of strings. We'll pass in our personnel. Let's see what we get. We get an empty array. Take last while. Oh, okay, so it does not ask, returns a new list containing the last n elements. Okay, but that is a key difference. We're not passing in a number of the things to take. We just say take the last things that all, like as long as they satisfy the predicate function, take it. If they don't, ignore it. This one has an E in it. What if we did like R dot ends with? You still get an empty array. Not sure why. Oh, but what if we get rid of this one and this one ends with an E? That's what it is. So, yeah. So it's checking the predicates. So Ron Crotty does not end with an E. So we don't take anything. But like we want to take all the last ones. So let's go back to includes. And then let's say instead of take last, let's take while. So Brubeck includes an E and Desmond includes an E. We're looking for lowercase e's. So Eugene, Joe, Jerry, Bob, Bates, but Joe does. Oh, and Joe does too. So actually, if we do this one, we should get back everything. But let's put Ron back. So we should get everything but Ron. And we do. We end with Joe. But if we did O, we'll get nothing. But if we did nothing other than A, something that's in at least both the first and the second one, capital D, the name includes capital D. We get Dave Brubeck and Paul Desmond. But Eugene has no capital D. Joe Dodge does, but it doesn't matter because we've stopped at Eugene because Eugene doesn't. Yeah. So, and this is why I don't use regular expressions because we have like starts with, ends with, um, lots of these different built-in methods and then arrays. And like regular expressions to me, and like maybe even behind the scenes, they're implemented where you break down a string into characters of arrays, and then you can just use array methods, or string methods on an individual character in the array. That's always been good enough for me. Um, so yeah, that's why regular expressions remain my Achilles heel, my kryptonite. But that's take last and take while. Take while does the same thing. I think, yeah, that's what we were just looking at. And then we get into a function that I find to be very unique because it's not pure. It does side effects, and that's what you need sometimes. So to demonstrate this, let's make a couple. We'll just do it all at once. We'll do a log, and we're going to pipe. And so we'll take an integer, we'll pass it to the pipe, we'll multiply it by 2. So we'll double it, and then we'll increment it, and you comma, and then we'll coerce it to a string using the string constructor. And then we'll call it with a 2. And we get 5, right? But what if we're debugging and we need to see what the value is? Well, we can use tap. And so tap takes a function that takes an A and returns anything. And then it takes an A and returns an A. So the tap function is almost like if we get rid of this um, predicate, or not predicate, if we get rid of this function here, A to A is the identity function. So if we pass, if A was a two, we get back a two. And if A was a four, we get back a four. Or Bob, we get back Bob. And this predicate, or I keep saying predicate, it's not a predicate. This function here is a side effect that's just like hitches on for a ride. Just like I know you're going to take a value and return that value, but in the meantime, can I take that value and run a side effect on it? And then you continue doing your thing. So formally, it runs the given function with the supplied argument or supplied object, and then returns the object, right? And it's saying object, but it could be anything. So what I could do is I could make a function called trace. And this is typically what I do with this. And that is r.tap. And the function that we're wrapping is log. So now this is a point free function. So it's taking a value and it's going to apply log to that value and log it here in the console. And that's all that does, except for it takes the value that we're passing to log and just returns that value unchanged. So let me demonstrate. So now if I use the trace function on our pipe and I run it, we get two, right? Because we're passing two into our pipe. So at this point, it logs two and then it just returns that value to multiply. So I think of this like visually, like if you had a pipe with a bunch of functions in it, like a physical pipe, and you could like take a nail and a hammer and make a hole in the pipe and you could see into the pipe. And I think that's where the idea of tap comes from. So then I can move my trace. In fact, I could just duplicate it and put it in between each item in here. And in fact, since I've done that, there's no reason to log it because that's what trace is doing. It's logging. So we can see the value before any transformations, the value after the multiply to, the value after it's implemented, and finally the value after it's been stringified. We can see each step, 2, 4, 5, and 5, the string 5, the numbers 2, 4, and 5, and the string 5. And this allows me to debug and like really easily because otherwise, like, how do you do it? And this is the problem with when you're doing method chaining, you're doing like 2 dot multiply by 2 dot increment dot string. Like that does the same thing as pipe, but there's no way to get in there and see what the value is unless you just stop it at the where you want to log. But normally when you log something, log returns void, like you don't get a value back, so you can't chain log, um, but you can here. So that's what tap does. Very useful. And you don't have to just log, you can run any side effects. So you could like send an email after each thing. Like, don't do that. But um, I think this is where you're going to find this to be the most useful. So that's tap. And let's check out test. Now we're back into string methods. The test takes a regular expression, oh no, and then a string, and it returns a boolean. And so test is built into the string array prototype in JavaScript. It determines whether a given string matches a given regular expression. So since I'm so bad at regular expressions, let's yoink this. And we'll just bring these into the thing. So Here we've got a regular expression, anything that starts with the letter X, and then we pass it the thing to test, and it's going to give us true or false back. And it says see also match because these are the two I get confused with. Test returns a Boolean, match returns like the result of the match. So XYZ, X is the first letter in the string, and that's what it's asking for. It returns true if X is the first letter, and false if not. So if I run this, we get true. And if I put a D here, we would get false. So it's just a curried version. We could say, I cannot type, starts with X. Starts with, I'm just going to say X and change these to capitals X, Y, Z. And we could say r.test and then pass in that regular expression. Starts with, okay, so that'll be false because it doesn't start with a lowercase x. It starts with an uppercase X. And it's false because I had too many arguments. Try that again. So that gives us true. And then if it was lowercase x, y, z, we get false. Yeah. So that's how that works. Really exact same. It's just curried with data last. And we've looked at match before, but let's just check it out again because it's related. And so if we did our dot match and we pass in our regex, starts with X, we get an array back. I don't remember doing this. Wait a second. We're getting a lot of stuff back. So it's saying capture groups are undefined. The input is XYZ. The index where it found it is 0 and X. This is like supercharged here. And that is not what we see in our examples. So that is strange to me. Pretty useful though. Let's use their example. Let's run that. That's what I was expecting to get. I don't know why. Oh, wait. Yeah, no, that's a regular expression. They're all regular expressions. But when I use this and ask what it starts with, I get this like several things. I'm not sure why I get that. But again, that's because I don't know my regular expression stuff so well. Yeah, that's interesting. If anybody has any information on why that's the case, there's comments below. You can use them. And let's just do a couple more before we get to these two functions, because like two, 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 two. Let's knock out Thunkify and times. The Thunkify is one that you probably don't use a lot. And I think it might have to do with the fact that JavaScript is an eagerly evaluated language, as opposed to something like Haskell, which is a lazy evaluation language. And what that means is that JavaScript is going to try to evaluate everything as quickly as it can, regardless if you're going to use it. So let's start here. It creates a thunk out of a function. A thunk delays a calculation until its result is needed, providing lazy evaluation of arguments. Yeah. So, when I was learning JavaScript, I was learning Svelte at the same time. And Svelte has a lot of callback functions. Um, and part of it is like you wouldn't run the function, you would just write it. So let me do some like pseudo element, like let's say we had a button and we had an on submit and we wanted to, this is the syntax for Svelte, and it's going crazy because I'm trying to write HTML in here. Maybe if I comment it, it won't be so angry at me. Yeah. Okay. So this button, and we would say on submit. So like when we submit like a form, for example, we could have a function called handle submit. And that works fine because, it doesn't invoke this function handle submit until we actually take the action and click on it, which is going to take longer in time. It's not going to, we don't want to submit the form when this code's being read. But if we passed parentheses to it and we invoke the function, as soon as the page loads, it's going to try to submit the form. Um, so we have to delay execution. So what we do, you know, we just don't invoke it, right? That's the easiest way to do it, like problem solved. But what if we wanted to pass data to the handle submit function, like pass an argument? And normally, let's say we want to pass 32 for some reason. Well, this would pass that value 32 to the handle submit function, but it would we run back into that same problem again. As soon as the page loads and it reads this code, it's going to try to submit, or it's going to try to invoke the handle submit function, because that's what parentheses do in JavaScript. Parentheses in JavaScript do three things. They group values together, like parentheses and please excuse my dear Aunt Sally. It provides a place to pass parameters when you invoke a function or apply a function to a value, but it also invokes the function. Um, since I have it open, this is pure script, which is essentially JavaScript, or essentially Haskell for JavaScript. And if I look for an example, oh, this is not a good example. Well, I'll just show you. In JavaScript, or not in JavaScript, in pure script or Haskell, if I wanted to call a function like add, and it needs two numbers, I just pass it like that. So like Haskell doesn't use parentheses, but if I wanted to like add two and three and four, add only takes two parameters, so I'd have to use parentheses to group them and do like well, in Haskell you could do it like this as well. I could first add two and three and then add four, but the parentheses just separating the values so it knows how to group things together. But in JavaScript, we use parentheses to actually invoke the function. So this doesn't work. So the way, if you needed to do this, you would use a thunk. And I just learned that this is the name. And it's just, we basically just wrap this function inside, excuse me, inside an anonymous function. So we're passing this function here, but we're not executing it. But when we click submit and it runs this function, the body of the function is this handle submit, and it's invoking it at that point with the value. So that's why we use thunks a lot. At least this is one example. We use thunks a lot in Svelte. The thunkify provides lazy evaluation of arguments. That's essentially what it does. It delays the execution of a function when you need to go ahead and provide the arguments of that function ahead of time, but you just don't want to run it right away. So thunkify takes a function, any number of arguments, and returns a k. And the only reason they're saying k is because that's the letter after j. So any number of arguments, and it just returns something. So this is the function that we want to thunkify. This returns a function. Yeah, the parentheses were throwing me off, I think. Here's the arguments, and then and then it returns a thunk. So see how it returns a function where the first argument is null, and then it returns the value, like the k that we're trying to do. So let's see if we can make sense of this example here. So what we're going to do is we're going to thunkify the identity function, and then we're going to pass the number 42. And then it's going to execute it. So it's a little complicated. I think it's because of the way we're invoking it like three times instead of once, and we're not logging it. Yeah, we get 42. So okay, because we're invoking it. But if we do it like this, let's actually name this const meaning the meaning of life or the answer to all question. Let's just call it function. And we'll thunkify our dot identity and then 42. So what we're saying here is that, the identity is going to give us the identity of the argument passed in. So identity of 42 is 42. But this is saying at some point, that's what you're going to give me, but just wait, slow down. So when do we actually get that? And that's when we invoke it. And so notice that we're invoking it with no arguments. And then we get 42. So let's inc. So we know we're going to get 43, and we've already passed the number to it. So inc 42. So like that's has enough, it has all the arguments it needs, which is one to go ahead and increment it. But we're saying don't do it yet. We're going to thunkify you. You do it once we specifically tell you to. So if we do a function like that, we're just going to get back a function. And if we get the length of the function, I think we get one or we get zero. We get zero. Um, but so that way we could say, hey, when I click a button, I want to get the incremented value of 42, but not until I click the button. And once you click the button, then it would invoke this function, and then you would get 43. That's Thunkify. So like Thunkify is actually really useful. Now in languages like PureScript, which is what I just briefly showed you a minute ago, or Haskell, it doesn't evaluate this function, which can make things like you can do things in Haskell and PureScript like increment, like map over a list and increment the values, but the list can be infinite. And you couldn't do that in JavaScript because it's going to try to increment that list as soon as you tell it to. But in Haskell, it'll just say like I want to increment the list, and we're like, okay, well, the list is infinite. We'll go ahead and increment the one, and then we'll like later on add a two and increment that one. Like it doesn't actually have to make the list right away, which could. eh, I've been explained by somebody who knows what they're talking about that with lazy evaluation, it's always just as fast as strict evaluation or eager evaluation, and then sometimes it's faster, but it's never slower. But that's not the world we live in JavaScript. So we live in the world where Thunkify is a thing that needs to be used in order to do lazy evaluation. And it says see partial and partial right, which we've already looked at, which is similar to curry. I don't want to go back to that. I just want to finish up with times. Yeah, I think we've done that. Hopefully, I explained this well. Um, if not, I'm sorry. And then let's finish up this video with times. And this is a pretty simple one. This is a list function. It takes an array with a number, or not array, it takes a function that takes a number and returns an A. And then it takes a number and that returns you a list of A's. So it calls an input function n times. That's the key. And it returns an array containing the results of those function calls. Function is passed one argument, the current value of n, which begins at 0 and is gradually incremented to n minus 1. How are you incrementing using negative? I'm not sure, but I'm going to use this example here. So log takes a number, sorry, it takes a function and then a number. So the function could be anything. Now I'm questioning this type signature. Every time I've questioned the type signature, I've been wrong, but that's okay. So this is the function to invoke, past one argument, the current value of n. N is a value between 0 and n minus 1, increments after each function call. If we passed in 5, 5 minus 1 is 4. And if we increment it, 6 minus 1 is 5. That confuses me. It returns an array containing the return values of all calls to function. Okay, so let's just work our way through this. So they're using the identity function that just returns the value that passed to it, and we want to do it 5 times. Oh, and then we don't pass anything else to it. So that's a little unique. Oh, R dot times. Yeah, so we get 0, 1, 2, 3, 4, 5. Okay. So it starts at n is a value between a 0 and it starts at 0. So we tell, give me the identity 5 times. So that's really what this is doing. This is just running a function however many times you want in a row. Value between 0 and n minus 1. Okay, I see what's going on. Increment has nothing to do with that. So the value of n must be between 0 and the number minus 1, which is 4, because it's going to do it 5 times. So the first one is 0, and the next one is 1, 2, 3, 4. So it's incrementing these numbers. That's what it means by increment. So let's say we want to multiply by 2 5 times. That's what's so interesting to me is that normally you would pass it some data, but here we don't pass it data. We just say multiply by 2 5 times. 0 times 2 is 0. Okay, 1 times 2. So I guess the data that you're getting, this like um, implicit data, is always going to be the number 0 up to n minus 1, which is 4 in this case, where we pass it 5. And then an increment starting from 0. So you're always going to start with 0. So this is always going to work on numbers. Like I can't pass Bob or a taco or something to it. So this is literally just saying the same thing as R naught multiply 2 5 times, and then invoke that starting at 0 and incrementing until it gets to the number you pass in minus 1, which is 4. And if we put some commas here and wrap this in a log, okay, this should be the same thing. And it is 0, 2, 4, 6, 8, except we don't get an array. We could if we just put it in an array. Yeah. And then we get the same thing as we got when we ran this 0, 2, 4, 6, 8. Yeah. I'm sure there's a reason to use that at some point. I'm kind of categorizing these functions in Ramda into different categories in my own mind. One of which is like built-in methods, but curried and data last, and then like necessary functional programming functions like curry, um, map filter reduce, and map filter and reduce are in both categories that I just mentioned. Um, and then like super useful functions like pipe and compose, I would say that's in category two, where you got to have pipe and compose if you're going to have a functional programming thing. And then there's stuff like flow, which is like you don't need it, but it's pretty useful. And then you've got like split, but then you've got split by, and like you don't really need a by or split by, but it's keeps you from having to build your own functions. Um, so we compose simple functions to make complicated functions, but sometimes we compose those same functions so many times that it just makes sense to include it in the library. And I was reading there an article from the one of the creators of Ramda, and it's difficult to decide what you want to include. And it's like, is it cool? And is it easy to implement? Like, we might as well implement it. But his idea is like, no, it needs to be useful a lot of times for a lot of situations across many different people's use cases doesn't really matter if it's simple to implement or not. That's the idea of like, why does it belong in Ramda? Because we could probably build a version of Ramda, a subset of Ramda with like 50 functions. And you might argue that that would be better because there's less functions to remember. Once you get into this many, it makes it easy to work with those functions, but it adds another level of complication to remember which function exists. So for example, the one we started with in this video, true. Like, does that really, do we need a true and false when we could just make a true out of r dot always true and then one for false? So I would say always, like the constant function has to be in a functional programming language. It just wouldn't make sense without it. But then we take that function, we make one called true and false, so I might argue that this is like, we don't need these two functions. And maybe they shouldn't be in here. But then somebody would argue back, but they're so easy to implement and it's so self-documenting. And we want to know if things, maybe it's very likely that people are very often going to want to be able to return true or false in the case where the thing that returns true or false needs a function and not a value, just the value true or false. It needs a function that returns true or false. So, I feel like Rambo overall balances that problem, if that's what you want to call it, very well. And I made my own version of something like Ramda called Query, and I abandoned it because I got out of control and just kept on adding things and adding things. And then you end up adding a function that you already added and you just called it something else. So now you got two functions that do the same thing. So I abandoned that project and started over with something called Canary JS. And that is a very much like Ramda, except more simple. All it does is handles functions that are already built into um, JavaScript, like the test. Anything that is on the string, array, object, Boolean, or number prototypes or lists. Yeah, array, I said that. Like all of those that are built in, I made Canary JS is a version of that that all the functions are curried. They're not auto curried, but they're just only curried. The data is always last, and that's about it. Um, and then I've added a few, like 10 other functions, like the always function, the identity function, um, tap, the tap function, the pipe function, compose, uh, and a few other ones, but that's it. Otherwise, it's basically a version of Ramda that's really easy to wrap your head around and remember what's in there or not because you've got this logical idea. Um, so I don't have Thunkify, I don't have times, um, because you could make this, but maybe this wouldn't be so easy to make, so maybe that would be a candidate to add. I'm just going to wrap up one more time, or just by looking. Yeah, so like you do have to do some things to make this times function. It's not as easy as like recreating the true and false function like this. And it's something that you might want to do. Like you might want to call something over and over again, but again, you could just call it over and over again. And you could loop, you know. So anyway, this is getting a little bit long, but now we're down to the two functions, to lower to pairs. Um, yeah, and then we're going to skip transduce. I'm going to get to it and traverse. Yeah, so I think we can knock out the rest of these T's in the next video, maybe, and I'll pick up in the next video with two lower. But thank you for spending your time with me. Tell a friend, and I'll see you in the next video.